Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This is the last in the series on the equilibrium of rigid bodies, and with the focus this time is sliding and toppling bodies. Let me remind you about an earlier object we considered. It was a child's toy, and it consisted of a solid cone and a solid hemisphere with circular bases of the same size stuck together, and they were made of the same material. On the basis of that, we calculated that the centre of mass of the combined object was on the axis of the cone, and the distance was actually 3/16 of a centimetre up. In other words, just to the left of the common face. Now if we put that shape down onto the solid plane like that, what happens? Well, we can see that the only place that the normal reaction could be acting is up that line, because there's only one point of contact there, and we'd have a weight force just to the left, and that would lead to a turning effect which, as you look at it, would be counterclockwise. So of course it would fall onto its side like that. Now that's a simple example of toppling, and you can see from that example how knowing where the centre of mass is will tell you what would happen. Well, now let's look at a related problem that looks at first quite different. Here we've got a rigid body which is a box resting on a plane. We're going to apply a force at the top right hand corner and ask what happens. Well, two things could happen. It could slide, as it has done there, or it could topple, as it's beginning to do there. Are we able to decide from what we know about centre of mass? And the answer is yes. So let's look at the problem with some numbers. We've got a box and it's got a mass of 10 kilograms. It rests on rough ground with coefficient of friction 0.3, and it's got height and width as given, and a force of p newtons is applied at the top. So we know now something about the dimensions. Now let me take you back for a moment to the previous slide. When you're in the position of toppling, if you think about the force diagram, the normal reaction force has to operate through that corner, and then it will be at right angles to the plane. Clearly it would operate upwards. That's important because we want to consider it just before it topples, which will be when the normal reaction force has just reached the corner. So in this situation then, we'll assume it topples first, and we'll analyse the force diagram. Now there has to be a friction force. There has to be a weight passing through the centre of mass. The force p newtons applied, and we've just decided that the normal reaction force must act through the base at that corner. Well, let's put the forces on. We've got 10g, we know that. If we resolve vertically, the two horizontal forces don't contribute, and we conclude that the only upward force has to be 10g as well. If we resolve horizontally, given that the force P is applied, we conclude that the friction must be P in the opposite direction. So with that diagram now, if we want to find out what P is, we'll need to do it by moments. So if we take moments about the point A, the virtue of doing that is that the 10g force, which is the normal reaction, and the p force, which is the friction, alike don't have any moment. So if we take moments about A, we'll have first of all the p force, which is counterclockwise, times the distance BA, which is the height of the box, 1.5, and that must equal the moment of the 10g. Now that's meeting the base halfway along the base, so that will be times 0.4. Now that simple moment calculation will tell us what P is. P is 4g over 1.5. Now the arithmetic starts to get a little bit tedious at this point, so I'll call in the calculator. Let's look on the next slide, which sums up where we've got to. We got as far as 4g over 1.5, so I've used my calculator and the g is 9.8, and we get 26.1 to 3 significant figures. So in that case we can say that the force will be 26.1 newtons if and when it topples. Well, on that basis then, the question we can ask now is, what's the maximum friction force? Because if our P, which is also the friction force, is bigger or less than that, that will tell us something about what's going to happen. So the maximum friction force is the 0.3, the coefficient of friction, times the normal reaction. So 0.3 times 10g is 29.4 when we use 9.8. Now if you compare the value that we got for our model with the maximum friction, we can see that we're okay. The friction that we predict is less than the maximum available. If it had been the other way round, if our calculation of 29.4 had produced a value, presumably because it was a different coefficient of friction, less than 26.1, that would say that as we keep pushing and P increases, it would reach the limiting friction before it reached the force necessary to topple it. So it's the comparison of these two values which tells us whether it slides or topples first. So basically what we did was assume it toppled first, find out what P has to be, and then compared it with the maximum possible P, and that allows us to decide. So our conclusion is that it topples first. Fine. Let's now think about something a bit more complex, but which will be clearly related. Now look at a box with no force pushing it, but rather it's on a plane whose inclination is increased. So there we are, a uniform cuboid, dimensions given, on a rough slope, and it's at an angle theta to the horizontal. So if we assume it doesn't slide, which means that the coefficient of friction is big enough for our purposes, we want the value of theta at which it starts to topple. Now that again means thinking about the force diagram. So there's the box. What can we say about the forces? Well, there'll be three of them. There'll be friction, there'll be weight, and there'll be the normal reaction. The friction's easy, that must act along the bottom edge and up the plane. The weight also is easy, that's got to act through the centre of mass. But what about the normal reaction? Now, thinking about what's happening realistically, it isn't that there's a normal reaction at one spot. If you've got a box on a carpet, it makes quite a big depression, so the normal reaction is actually spread over lots of little forces perpendicular to the surface, the common interface, the surface of the bottom. But just as we can replace the forces on a rod, which arise from weight on each of its particles, by a single force through the centre of mass, in the same way we can consider that the normal reaction acts at one point. And we saw that in the previous problem where it acted at the corner, though that was easier to justify. But here we can see that we can put the normal reaction in one place, but we have to decide where. Now if we put it anywhere other than going through that point where the F and the W intersect, we would find, if we took moments about that point where I've put the blue spot, that the normal reaction would create a moment which is unbalanced by anything else, because the F and W go through the fulcrum. So we've really got to put the normal reaction through that point as well to have equilibrium. So our force diagram looks like that. Okay then, what happens when we increase theta? Well, the box clearly would start to rotate in a counterclockwise sense as we look at it. W would still act through the centre of mass, which I'll mark with a G just for reference. But as the box swings, this blue spot where W cuts the base would move across the bottom and finally reach the corner, and it would take the normal reaction with it, just by using the same arguments. If we tip beyond that point, we'd really be implying that the normal reaction is acting beyond the surface, the common interface of the bottom and the plane it's standing on. That's not realistic. So we conclude that it's going to topple at precisely the point when it's tipped far enough for that blue spot, the point of confluence of those three forces, when it's reached that bottom corner. So we analyse it then on that basis. So there's the two diagrams. This is demonstrating in the physical context. That's like a kind of attempt to represent what a photograph would look like in section. And here's the force diagram. We've got the normal reaction acting up this edge, and we've got the weight passing through the centre of mass vertically downwards through this corner. So that's where our analysis comes. Now the theta, which is the angle between the plane and the horizontal, reappears in the diagram there because that's 90 minus theta, so's that, so there's theta again, and it will appear finally on the force diagram up in that corner. And that allows us to work out what theta is, because we've got the dimensions of the box. So the tangent of theta will be the base measurement over the height measurement. So there's tan theta is 0.8 over 1.5, and we work that through using the calculator to get the angle 28.1. And that's the maximum angle that you can get when you tip it, and that's the point at which the box will topple. So there's our answer, 28.1. And on that note, we finish this particular presentation. It's the last one of this series of 4 on the equilibrium of rigid bodies.